All right. Indefinite integrals have no bounds on their integrals. Definite integrals exist on a certain bound. As long as we can find the antiderivative, we can find the area under the curve. And that's exactly what this means. The integral of f prime is f. So I take it from my upper bound minus my lower bound, and that gives me the area. What is this thing really doing for us? We have some function f of x. We're within some interval, some bound. We want to find the area between the function and the x-axis, between the left and right limit bounds. We want to find this area. How do we find the area? Area is base times width, or base times height. The base is defined by delta x. Which is b minus a, or x2 or xn plus 1 minus xn. The height is the function itself. That's the area of each one of these. So what we have to do is we have to add up all these small area rectangles and add them all up. I use C of k because C of k is the average, the midpoint of each of these intervals. That'll give me a better picture. Now we take the limit. Let's make this go to n. As n goes to infinity of the summation of our function. This is our area. Have we seen that before? That's the Riemann sum. That looks pretty boring. There's limits, the summations, a whole bunch of work. We can go a lot faster by using the integral method. So we have our function, a composite, well, not yet. We'll do that in a second. So we have our function. That's the way we've been doing it. This setup is from our function to the x-axis. That's the area we're looking at. What if we had two functions and we want to know the area between them? This is f of x, and this is g of x. This is a, and this is b. I want to know this area. How am I going to find it? Think of what what the integrals find for us. What does the integral of f of x find for us? The integral of f of x finds everything from the f function, from the top function, all the way to the x-axis. Right? What does the integral of g of x find? It finds everything below the g down to the x-axis. So how do I get this area? Yeah. To get this area, I've got to take f of x minus g of x. What if we had a composite function? F of g, f of x, and g of x, yeah, those are pretty easy equations. What if we had a function f of x, g of x? This is what we found out earlier. Does this look familiar? Let's make it easier for you. If we had a function like this, what would my u be for substitution? U would be the inside function, wouldn't it? What would my du be? G prime of x dx. Well, this is f u du. Because now once we're in that form, then we can just integrate them and take the upper bound minus lower bound. And there we have it. Because what we would do next here at this stage, we'd find the integrals. Let's call it capital N. And then that would be f of b minus f of a. So that's what we just did. Now we're going to have specific bounds. We're going to have answers. We're going to have specific answers. Let's look at our first example here. Example 1. Evaluate this equation. So how would you do it? What's my first step? We have to find a u. What's our u going to be? X cubed plus 1. So once we found u, we have to find du. 3x squared dx. Do we have a 3x squared dx? Yeah, here's a 3x squared. There's the dx. So that's the du part. And there's our u. So we have the square root of u du. convert the radicals into exponents. Now we integrate. The integral of that would be u 1/2 plus 1 over 1/2 plus 1 from -1 to 1. U to the power 3/2 over 3 over 2 from -1 to 1. Reciprocate the bottom. What is u? X cubed plus 1. From -1 to 1. Now what do? Start with the top one. We have, well, leave the 2/3 out in front. It's a constant. So I take the 1, put it inside the equation, minus the -1 inside the equation. Brackets. So this is my x equals here and x equals here. That's what I put in the formula. So we have 2/3. 1 cubed is 1 plus 1. -1 cubed is -1 plus 1. That one goes to 0. One plus 1 is 2. So it equals to 4/3. Nuts. I forgot the exponent. 3/2. Three-halves. So this is 2 over 3. This becomes 1 and 1/2. So it's 2 square root of 2. That. So far, so good. Yeah, I forgot about the exponent, which is pretty integral, as you can see. All right, let's look at example 2. A, the integral from pi over 4 to pi over 2 of cotangent theta, cosecant squared theta, d theta. So here is your tough question. Which one's going to be u? Because once you find u, take the derivative of it, and hopefully it's the other one. So look at the functions and see which one has. Does cotangent have cosecant squared as a derivative? It does? Okay, so that made it easier for us.
Sorry, they had the.
What's the derivative of cotangent? Yeah, so it's negative cosecant squared. which I want a cosecant squared. Because the derivative of cosecant squared would be 2 times something, not cotangent. So. So cotangent is my u. My du is cosecant, negative cosecant squared. So I need a negative in front of there. So I need a negative out there. Okay, here's the thing about it. Okay, I'll show you another way here. What's the integral of u? The integral of u is u squared over 2. Negative. The negative still out in front. Integral of that one is u squared over 2. U is cotangent squared beta over 2. Now we plug in our points. So we have cotangent squared of pi over 2 minus negative cotangent squared pi over 4 over 2. At pi over 2, what's cotangent? Cotangent is sine over cosine. No, it's cosine over sine. Because tangents. At pi over 2, cosine at pi over 2 is 0 over 1, so this is 0. Negative and negative has a positive. Cotangent pi over 4 is going to be 1 because they're both the same signs. Sine pi over 4, cosine pi over 4 is 1. So the answer is 1/2. Now, there's another way. Let's try this other way. When we did the substitution, when we had the whole equation with respect to u, are these bounds with respect to u? They're with respect to cotangent and cosecant. So what we can do here is once we had u du, we defined u as cotangent. What would it be at pi over 4? So what is u at pi over 4? Pi over 4, they're both the same. Square root 2 over 2 over square root 2, which is 1. So this means our new bound with respect to u is 1. And it's supposed to go up to this. This used to be pi over 4 on the bottom. It used to be pi over 2 on top. What is the cotangent of pi over 2? That's 0. So if you use substitution, you can either leave your bounds the way they are originally and at the very end reverse them, or when you convert to u, convert the bounds also. Take the lower one, put it inside here. Take the upper one, put it inside there, and see what your new bounds are. So let's see what happens here. The integral of u is u squared over 2 from 1 to 0. So we have negative 0 squared over 2 minus negative 1 squared over 2. That's 0. That becomes positive, so we have 1/2. Same thing. So we can change the bounds of integration to be relevant to the transformation of cotangent to u. All right, let's look at B. The integral from pi over 4, negative pi over 4 to pi over 4 of tangent x dx. What do we know about this? We know that tangent is sine x over cosine x. At pi over 4, sine and cosine have the same values. Minus the negative sine pi over 4, what's that going to give us? So what's our u going to be? U is going to be cosine. Du will be negative sine. So what we have here, we need to have a negative in front of the sign, so we have to put a negative out in front. So it's du over u. Let's change the bounds of integration. Cosine. Cosine of negative pi over 4 is what? Because remember, cosine is an even function. So if it's a positive theta or this negative same theta, it'll give you the same answer. It'll give you the same x value. At pi over 4, what is cosine? Same thing. Du over u is ln, absolute value of u, from radical 2 over 2 to radical 2 over 2. So we get negative ln radical 2 over 2. Like, that can't be negative, so it's okay. Minus a negative ln radical 2 over 2. This becomes plus. It equals 0. Well, we knew that. We could have stopped that a long time ago. Right here. The bounds of integration are the same value. There's no domain. So there's no area between a single line. Now, what does this tell us? If the integral is 0, what does that tell us? Because remember, our original equation was this. What it's actually is telling us is from negative pi over 4 to pi over 4, tangent x dx is equal to 0. Because this still relates back to the original equation. What this tells us is from negative pi over 4 to pi over 4, equal areas. One's negative, one's positive. When you add those two together, you get 0. So that's what it tells us. Which tells us that tangent is an odd function. Remember what odd and even functions meant in algebra? Ooh, we're getting past time. Remember what odd and even functions were in algebra? An even function is if I had an x value, it equals some y value. I get the same value if I put a negative x in there. It's symmetric about the y-axis. That's an even function. So f of x equals f of negative x. An odd function, if I put a positive x, I get a positive y. If I put a negative x, I get the same negative y. It's symmetric about the origin. So if I put a negative inside there, I get the negative y value. And we'll pick up here next time. I'm so sorry, everybody. Okay. Which means we're pretty close because